Today I'm going to talk about finite fields, and the overarching goal for today is to describe all of them. We say that a field is of finite order if it has a finite number of elements. So let's recall what we know about finite fields. So if K is a finite field, then we can immediately observe some simple properties. First, K is necessarily of finite characteristic. So P, which is the characteristic of K, is a prime number. It cannot be of characteristic 0, otherwise Q would be contained in K, and Q is not finite. So then recall that fields of finite characteristic have prime subfields of the form Fp, which is isomorphic to Z mod P, is then the prime subfield of Q, of K. And therefore, K is a finite dimensional Fp vector space. So the number of elements in K is equal to the number of elements in Fp to some power m. Because we can represent vectors in K as tuples of elements in Fp, and for every coordinate we have p choices. And if we have n coordinates, then we would have a total of p to the power n choices for vectors in K. So a field of order Q, this is how we usually denote a power of p. So a field of order Q is usually denoted by F sub Q. And a spoiler for the rest of the lecture, that we will prove that for every power p of p, there is only one Fq up to an isomorphism. And we can build examples of finite fields by taking an irreducible polynomial of some degree n with coefficients in Fp. Then Fp mod out by F, by the ideal generated by F, will be a field, and the number of elements will be exactly p to the power n. So the order of the field is p to the power n, because this is a field extension over Fp of degree n. We considered more explicit examples. So we worked with F4, which was F2 adjoint x mod out by the equation x squared plus x plus 1. And I recently considered F8, which was F2 adjoint x mod out by x cubed plus x plus 1. So now I'm going to start working towards the result that I announced. And for that I will fix a prime number p, and q will denote some positive power of p. So theorem number 1, if K is a field of order Q, then firstly, every element of K is a root of the polynomial, which I denote by E sub q of x. It is a polynomial of degree q, x to the power q minus x, which is a polynomial with coefficients in Fp. And moreover, the group of non-zero elements, k minus 0, is cyclic. So k cross is a cyclic group of order q minus 1. So how do I prove this? For part A, I observe that K cross is an Abelian group of order q minus 1. So this is the easy part of the statement in part B, which means that every element alpha in K star has that its order divides q minus 1. So for every alpha in K star, alpha to the power q minus 1 is equal to 1. Or equivalently, I can say that alpha to the power q minus alpha is equal to 0. So we proved that every non-zero element of K is a root of E sub q. But 0 is also trivially a root of E sub q because we have that 0 minus 0 is equal to 0. So part A is good. Now to part B. So we know that K star is a group of order q minus 1, so we want to show that K star is cyclic. So I claim that by the structure theorem for abelian groups, I can arrange K star into a direct sum of abelian groups C1 through Ck, where each Ci is a cyclic abelian group of order, let's say, di, and their orders divide each other. So d1 divides the order of C2, etc., and all of them divide the order of dk. So proof of claim. By the structure theorem that I proved, I can arrange K star into a direct sum of Z of cyclic groups of order some prime power. So Z mod P1 to the power A1I1. So I move all the powers of P1 to the first summand, and so that all the other primes are different from P1. And I have that these groups are isomorphic to Z mod P1 to the power A1I1. Then I pick some other prime, let's say P2, and I take all of the summands, which are obtained by taking quotients by the powers of P2 here. So I have A2, I2, the sum over I2, etc. So from each of these big summands, I can take the largest power of this prime, and I say that I can arrange Ck to be Z mod P1 to the power A11, assuming that I1 is the largest in the first big summand. And I take Z mod P2 to the power A21, where I assume that A21 is the largest among these powers, A2I, etc. And since all of these primes are distinct, they are also mutually coprime. So by the Chinese remainder theorem, I get that this is isomorphic to Z mod P1 to the power A11, P2 to the power A21, and so on. And so when we split off all the largest powers of the primes, we get Ck. And so when we split off the next largest powers of these primes, we get something that would divide the order of Ck. So we arranged it so that dk, which is the order of Ck, would be divisible by all the other orders in this sum in this sum. So now from this claim, I can observe that for every alpha in k star, the order of alpha would divide dk. And this is because alpha can be represented as a sequence of elements, as a tuple of elements from C1, C2, etc., Ck, and each coordinate in Ci has order that divides dk. So the order of this whole tuple would divide dk, and as a consequence, the order of alpha divides dk too. And so we get that every alpha in k star is the root of the polynomial e sub dk plus 1 of x, which is x to the power dk plus 1 minus x. But we know that over fields, a polynomial cannot have more roots than its degree. And so we have that the number of elements in k star is q minus 1. Number of roots is q minus 1 plus 0, which is also the root, so it is q. It should be at most the degree of e sub dk plus 1, which is equal to dk plus 1. So now, if I assume that k star is not cyclic, then dk is strictly smaller than q minus 1. And so I get that from this inequality, I get that q is at most dk plus 1, but also dk is strictly smaller than q minus 1, so this is smaller than q, which is a contradiction. And therefore, k star should be cyclic. And we'll prove the second part of this theorem. Now I can formulate the existence theorem. Theorem number 2. First, there exists a field of order q for any q which is a prime power. And second, all fields of order q are isomorphic. For the proof of part A, I consider a certain polynomial, the polynomial e sub q in fp adjoint x, and I view its splitting field L, which is a field extension of fp. So in particular, e sub q splits completely over L. So it has exactly q roots in L. I claim that the roots of E sub q in L form a subfield. And for the proof, I take, let's say, alpha and beta, roots of E sub q, which means that alpha to the power q is equal to alpha, and beta to the power q is equal to beta. So now I want to check that the same holds for alpha plus beta. So I view alpha plus beta and I take it to the power q. Because q is the power of p, and p is the characteristic of the ground field, I get that alpha plus beta to the power q is alpha to the power q plus beta to the power q. But alpha q is equal to alpha, and so I get that this is equal to alpha plus beta, which means that alpha plus beta is a root of this polynomial. And similarly, alpha times beta to the power q is equal to alpha to the power q times beta to the power q. And from these equations, I get that this is equal to alpha beta. So the product of two roots is also a root. And because the splitting field is the smallest field that contains the roots of E sub q, I get that as a corollary, I get that L has exactly q elements. So L is a field of order q. And now I want to say that all these roots are distinct. And for this, I will need the following fact, which will be an exercise. And the fact is that a polynomial f of x with coefficients in any field has a multiple root alpha if and only if its formal derivative f prime of x has the same root. And now I use this fact, I apply it to the polynomial E sub q. E prime of x is equal to this. So q times x to the power q minus 1 minus 1. Q is a multiple of p, so it is equal to 0 over fp. So I get that the formal derivative of E sub q does not have any roots. And in particular, does not have any roots in common with E sub q. So all the roots of E sub q are distinct. So E sub q has exactly q different roots in L. And this corollary should have been here. So up to this part, we proved that L is equal to exactly the set of roots of E sub q, but we didn't know if E sub q could have less roots than q. And here we proved that L has exactly q elements. And now I'm showing that any two fields of order q are isomorphic. So let's say that K and L are two fields with q elements. We know that K star and L star are both cyclic groups. And let's say that alpha is a generator for the group K star. So that K is equal to Fp adjoint alpha. Then we can take the minimal polynomial for alpha, F, alpha over Fp. And this is an irreducible polynomial. Of degree equal to the degree of this field extension. K over Fp. So we know that K has order q, and q is p to the power n, so the degree must be equal to n. Okay, so we know that E sub q of alpha is equal to 0 by theorem 1a, because alpha is an element of a field of order q. So E sub q lies in the ideal generated by F. Which means that F divides E sub q. But E sub q splits completely in K, in L, because L has q elements. So E sub q has exactly q roots in L, and so it must split over L. And since F divides E sub q, so F is a factor of this polynomial which splits completely, then F also has a root in L. But by characterization of minimal polynomials, the minimal polynomial of beta over Fp is equal to F, because F has beta as a root, and F is irreducible over Fp. and it then follows that K, which is equal to Fp adjoint alpha, and because we know the minimal polynomial, we can express this as a quotient of the polynomial ring. But by this equality, we can also say that this is isomorphic to Fp adjoint beta, which is a subfield in L. But we know that K has Q elements, so Fp adjoint beta also must have Q elements. And so this subfield coincides with the whole L. And so K is, by this chain of isomorphisms, this is isomorphic to L, because this must be in fact an equality here. We can quickly observe from the way we proved part B of Theorem 2 that for every prime p and for every positive integer n, there exists an irreducible polynomial of degree n over Fp. So the way that we show it, we have that K, we take a field K of order Q, we know that it exists, so we take some element that generates the cyclic group of this field and take its minimal polynomial. And by viewing and comparing the degree of this minimal polynomial with the degree of the field extension, which must be n, we get that f is an irreducible polynomial of degree n. And the last theorem describes when we have homomorphisms between finite fields. So we know that the only homomorphisms between fields are inclusions, and I claim that f sub p to the n is contained in, or can be mapped to f sub p to the n if and only if m divides n. So the proof is in the forward direction that assume that we have such an inclusion, then Ef sub p to the n is a vector space over f sub p to the m, which means that there exists some number a, so that f sub p to the n is isomorphic to f sub p to the m direct sum a times as vector spaces, not as rings or fields. And then we compare the number of elements. So the number of elements on the left hand side is p to the n. The number of elements on the right hand side is p to the n, is the number of choices for each coordinate, and we have a coordinates. So we have p to the power ma. So n is equal to am. And in the other direction, suppose that m divides n, then p to the n minus 1. I can do p to the n as p to the m to the power a minus 1, and then viewing this as one symbol, I can write it as p to the m minus 1 times the sum of p to the m to the power a minus 1 to the power a minus 2, etc. p to the m plus 1. So in particular, I get that p to the power m minus 1, which is the number of elements in the field, number of invertible elements in the field f sub pm, divides p to the n minus 1, which is the number of invertible elements in the other field. So we know that f sub pn, the invertible elements form a cyclic group. And we can say that it is generated by an element alpha. So some power of alpha has order, has order p to the m minus 1. So let's say that this is beta. Then the set of elements 1, beta, beta squared, etc., beta to the power p to the m minus 2 and 0. So all these elements are roots of the polynomial e sub p to the m. So and we observed that if we take roots of this polynomial, just as in theorem 2 part A, we get a subfield. And moreover, because we know the order of beta, so we know that there are exactly p to the power m roots of this polynomial. And so we got an inclusion of f sub p to the m into f sub p to the m, using the fact that m divided m.